Right, so question two. Video cut off the last one. Yeah, question two. This is our conversion factor here. So obviously, one of the thousands cancels. So the actual conversion factor is 1,000 over 3,600 squared. So the answer is A. Okay. Question three. Right, it's a very. This is a standard velocity time graph. You'll see a lot of this at A level. It's the bouncing ball graph. If ever you see a sawtooth shaped velocity time graph, it's a bouncing ball or something oscillating on a spring. Anyway, balls drop vertically into the horizontal surface and it bounces twice before being caught. Obviously, we have first bounce here and second bounce here. What's happening here? The velocity is positive and then it suddenly becomes negative. This is when the ball reaches maximum height. Okay. Other things to be aware of with this: the gradient of these sections is always constant because the ball is always accelerating at 9.81 meters per second squared. So acceleration is constant when the ball is in free fall, either moving up or moving down. The acceleration is always 9.81 meters per second squared downwards. Right. Another important thing to notice: the ball is dropped. So it's dropped from its maximum height and it will initially start to fall. Now, the first section is negative. So that tells us that downwards is negative. Okay? So if downwards is negative, the acceleration must be negative. Okay? The acceleration when the ball's in free fall must be minus 9.81 meters per second squared. So that eliminates this graph and eliminates this graph, doesn't it? Because in these graphs, we can see the acceleration is positive. Okay? So all three graphs, the acceleration is positive. Now we have to take into consideration the bounce. This is where there is a sudden, almost instantaneous upward acceleration that causes the ball to change direction, start moving upwards. So that has to be C. So the answer is C. Easy one, that. That should have been fairly straightforward. Question four, potential difference. We've got a conductor. We've got drift velocity. Now, always nice to draw a diagram, just a cheeky little diagram. There's our conductor. Okay. What's going to stay constant? Well, obviously the dimensions of the conductor are going to stay constant. But what if we change the applied potential difference? Right. What's the equation? What is the drift velocity equation? So it's I equals NAVE, where N is the charge carrier density, A is the cross-section area, V is the drift velocity, and E is the charge on an electron. Right, now I have a little bit of an issue with this question. It doesn't state that it's an ohmic conductor, and it doesn't state that it's kept at a constant temperature, does it? Which I think it should have done. But I'm going to assume that's what they meant anyway. So if it is an ohmic conductor, if it's kept at a constant temperature, then we can say that V is proportional to I. Now, if V is proportional to I, then V is proportional to NAVE. Now, charge carrier density is going to be constant. Cross-section area is going to be constant. Charge on an electron is constant. So we have to say with a fair amount of certainty that the applied potential difference is directly proportional to drift velocity. So the answer is C, isn't it? Okay. Very straightforward, that one. If you assume to make the assumptions I just mentioned. Well, we've got a plane travelling. It's vector addition, isn't it? Okay, so you have to draw a diagram here. Yeah, without question. You can't. Please don't do this in your head. But just draw a quick cheeky little vector addition diagram. So we want to fly due north. We've got two vectors. We've got a velocity vector to the west. We've got a velocity vector diagonally like this. So we need to draw what's going on. So let's have a little look at this. We've got 7.5. Not going to write the units here. We've got 7.5 there. We've got the diagonal, which is 42 meters a second, like that. The resultant, which is the what the direction and speed the actual plane does travel at, has to be due north like that. So let's call that the resultant velocity. Okay. Now the angle, it wants to know the angle the plane turns through. So that is going to be this angle here, theta. Okay. The plane was flying due north. It has to move to that angle. So it's just a trig identity now, isn't it? So using our trig superpowers, we've got, so it's this one here. Here's our triangle. Okay, here's our angle. So there's the hypotenuse. There's the opposite. So it's sine, isn't it? Sine theta is opposite over adjacent. So it's 7.5 over 42. Theta is sine to the minus 1, 7.5 over 42. So the answer is B. Okay, I cannot stress enough the importance there of drawing a vector diagram. Okay, even for a multiple choice, you're going to have to sometimes do calculations and draw diagrams. Okay, question 6. We've got an ohm meter. Okay, again, we're looking at the resistance of a wire, an ohmic conductor. It's nichrome. We're talking about resistivity here, aren't we? Now, we want to find resistivity from the gradient. We want to plot a graph where the resistivity is equal to the gradient. So there you go. So gradient of the graph equal to resistivity. Right, what's the equation for resistivity? Well, for a wire, resistance is directly proportional to length. Resistance is inversely proportional to cross-sectional area. The constant of proportionality is resistivity rho. So it's rho L over A. Rearranging that, we get, so resistivity is RA over L. Okay. Now, if we want the gradients to be exactly equal to resistivity, we're going to have to plot RA on the y-axis and L on the x, because this has to be the gradient. So RA on the y and L on the x is D. Question 7. Fairly straightforward, that one. Question 7. A meter rule was used to measure L, so it's the same practical, the resistivity practical. Right, what do we got here? Well, obviously we know there's a fair few different ways of estimating the uncertainty in a measurement. You can have the resolution of the measuring device, but if you see repeat measurements, as we can see here, then it's range divided by 2, isn't it? Okay, it's range divided by 2 only if that gives you a bigger uncertainty than the resolution. So what's the range here? So the range, what's the biggest? 89.6, and the small one, 89.1. So the range is 0.5. So the uncertainty in L is 0.5 over 2, which your calculator will say 0.25, but we have to use the same number of decimal places. Okay, so we have to round up to 0.3. Okay, with uncertainties, we always round up. Okay, so the uncertainty in L is 0.3 centimeters, which I believe is C. Okay, last but not least, question 8, even the multiple choice at least. This is marks in the bag. You should be able to see that if we've got the force at an angle, but it's actually moving horizontally, then the force, or the component of the force rather, that's in the same direction as the motion is this one here. So that component there is F cos theta. So work done is force times distance, but it's the force in the direction of motion multiplied by distance. So that is FD cos theta. The reason why I said that's marks in the bag, because that is a standard equation for calculating work done, which you should know off by heart. Okay, so that, like I said, marks in the bag. Correct answer is B. Okay, that's the multiple choice. Next video, I'm going to go on to question 8. Thank you.